Thank you, everyone. Welcome back to Grad Chat, brought to you by PhD Balance. My name is Susanna Harris, and if you're brand new to watching the show with us, welcome. And if you've been here before, welcome back. We kind of dedicate this space to talking with different people who are in different places of working in academia, have worked in academia, but who are willing to talk about some of the things that maybe we don't get a chance to talk about while we're actually working in our labs or inside of our universities, but are so common to students. And so I'm going to kick it over to my amazing co-host to introduce our guest for the day.
Welcome back to Grad Chat, everyone. So our guest today is Abe Asfaw. Abe is completing his PhD at Princeton University, focusing on experimental quantum computation. And in addition to working on his PhD, Abe's goal is to build diverse quantum communities all over the world, including his home country in Ethiopia. So currently, Abe leads a global education and open science advocacy mission for IBM Quantum. And beyond IBM Quantum, Abe has contributed to the development of quantum education at the US national level. So welcome, Abe. It's so exciting to have you here. If you want to say a little bit more about what is quantum and how did you get interested in all of these amazing efforts that you've been involved with?
It's really cool to be here and to be talking with you. What is quantum? This is a very hard question. Let's start with the hard stuff.
At least we didn't ask what is computers.
So let's think about it this way. So when I finished undergrad, right about the time when I was thinking about applying to grad school, I knew I liked electrical engineering, physics, math, and truly was just the most indecisive person. I had no idea what to do with this mix of things. And it felt like picking any one of them would sacrifice other interests. So I had no idea what to do with this. And a professor at the time who saw me going through this suggested, hey, there's this really nice interdisciplinary thing that you could study that mixes all of these, and it's called quantum computing. No idea what that is. So I started learning about it, and I learned, the key thing that I learned is that computation as we've known it, whether you're talking very far back like the abacus or adding things with putting objects together, or even the computers that we use today, like the laptop we're using to talk today, are all classical computers. They're built on the principles of classical physics. So at the end of the day, you're working with bits, zeros and ones, and you're building logic off of those bits. Quantum computers ask a different question. The motivation here is, if you're trying to understand more about nature, if you're trying to simulate how, for example, atoms, molecules work, at that level, the rules of physics that are in action are quantum mechanics. Quantum physics is at play there. But the question now becomes, can you leverage a quantum system for computation from the ground up instead of working with bits that are zeros and ones? So instead of using switches that switch between zeros and ones, can you fundamentally rebuild a computer from the ground up using quantum mechanics and the rules of quantum mechanics? And that's what quantum computation is trying to do. And the best part about this is that quantum computers are actually a physical existing thing today that you can work with.
That was literally going to be my question. I was like, okay, but this is a great idea. So does it work though? Does it work? Does it do things? I don't think I've ever played with one.
Yeah. So I remember back in 2016, I was in lab in the clean room, actually. I remember it very well because, well, you'll see. In 2016, I remember making devices. So making these quantum computers at the end of the day is all about, first of all, in a research lab, patterning the quantum computer on a small chip. And then usually for at least the quantum computers I studied, you need to cool them down to very cold temperatures to get them to work. And so the grad student experimental routine is something like go to the clean room, make your device, and then come back to the lab, package your device and wire it up, and then cool it down in a fridge, and then run your experiments. And I remember being in the middle of this routine in 2016 and finding out, hey, these researchers at IBM just put online a quantum computer. And what that means is like they're able to do the same things. They're able to make a quantum computer, but then all the control electronics that's needed, they wired it all to the internet. And now people from all over the world can actually run things across the internet on these quantum computers. And I remember thinking, wait, so I'm trying to make one here right now, and these things are available online. And this is going to change the way quantum computing works. This is going to change it from being something where you need access to a lab, like I was trying to do, to something that anyone can work with today, something that anyone can participate with. And so the answer to your question, Susanna, is yes, these things exist, and they've existed for a little bit over 4 years now online. And so it's not just you and me, but really anyone from the world with an internet connection who can run things on these quantum computers.
Okay, I would break it though.
The thing is, at least with the quantum computers that I've studied, they're usually enclosed in fridges. So because you need to work in very cold temperatures, they're enclosed in several layers of protection.
Okay.
So you can listen to like music in the lab and so on, and you're not really affecting things so much. But yes, if you really wanted to, you could probably break one of these.
Oh, I don't. I would not really want to. It would just be... I'm just bad at. And actually, we have a question from one of our regular viewers, Rob, asking if everyone is using one, doesn't it slow it up? You know, like how does? And I know that you have a demo for us. Can we see it?
Yeah, sure. I can show you a demo, but to answer Rob's question, the reality is yes, you can run things on these quantum computers, and the fact that everyone can run on them means you have to stand in line online. And I actually have a demo where I'm standing in number 3 in line to be able to run my quantum circuit right now. So I can start sharing my screen and show you how simple it is to get started. Really, at the end of the day, I'm just writing Python code and building out quantum circuits.
Yeah.
So one cool thing that we can do is I can show you a demo, but I can also show you how, remember when we talked about like zeros and ones and building out the quantum logic, like the rules here are different from classical physics where you're building out logic of zeros and ones. I can show you how that logic also works in the process. It's a really cool exercise, and I can show it to you.
Yeah.
Let me just start sharing my screen, and hopefully I don't mess this up. I've been known to do that before.
Well, it's good. That makes me feel a little bit better that you're about to show us quantum computers, and screen sharing is tricky.
Hopefully I don't break one in the process.
I totally would have jinxed you. I won't say anything. Ooh.
So you should be seeing something that looks like Python code because it is Python code. Is that what you're looking at right now?
Yep.
Yep.
Yeah, so the code, again, should look very familiar. I'm using Jupyter and writing Python code, so this should look familiar to a lot of people. And at the end of the day, I'm just writing down, bringing in a few imports. So the quantum computing software that I'm using is called Qiskit, and it's open source. So if you see some problems with it, you can go modify it and help the whole quantum computing industry, which is another really cool thing. But anyway, I wanted to show you some really cool things and then also show you how I'm running on the quantum computer. And to Rob's point, also how there's a queue where you have to wait in line. So first things first, this is going to be like a series of Lego bricks that I'm going to put together. So tell me if the Lego bricks are making sense. And this is like the first way I learned about how things make sense in quantum computing. So hopefully it makes sense. But here. Okay, just let's do this. This is the fun part. So let's build out a quantum circuit. And a quantum circuit at the end of the day in this picture that I'm going to show you is just a qubit, which is a quantum bit. So just like the zeros and ones, the bits that we work with on a classical computer, here I'm creating a circuit which contains one qubit, and I'm just resetting that qubit. And so the circuit, when I draw it, looks like this. It's just a qubit with a reset on it. And I'm saying that reset should reset it to the 0 state. one immediate thing you'll see in quantum computing is that the way people write down the states of these qubits using this notation with an angle here and a straight line here. Don't be intimidated by that. It just means this qubit is in the state 0. And in fact, if you simulate it, you see that the qubit is in the state 0, which is not too surprising. Now, this is you've just built a quantum circuit, and the exercise of running things on quantum computers boils down to building these quantum circuits and then putting algorithms into these quantum circuits. So we're in the phase where, with classical computers, with the computers that you have today on your laptop, you write high-level language to be like Python to be able to describe how you want things to work. But at the end of the day, they boil down to instructions on bits. And here I'm describing those instructions on the bits. So if I apply this reset operation, it's pretty straightforward that I get a 0 here. But now if I apply another Lego brick, this new Lego brick that I'm introducing into the picture is called an H, which is short for a Hadamard. You see now after I reset, if I apply that Lego brick, what I see is a quantum state that is both 0 and 1. This is starting to be now something that you can't do on a classical computer, right? Like equal proportions of 0 and 1 here. Now, the interesting part about all of this is that, again, look, I'm just writing Python code. I'm just applying a gate and I'm drawing, and this is the familiar routine that we all do in Python. The really, really cool part about all of this is that once I'm able to create zeros and ones, I can also introduce another brick. So this time, the new Lego brick that I'm introducing is called an X. And this X gate will take you, again, reset and apply X will take you from 0 to 1. So it takes all the weight from the 0 state to the 1 state. So I just showed you 3 pieces, right? I was able to reset to the 0 state. I'm able to create 0 and 1 with equal proportions, and I'm able to create 1. So let me ask you now at this point, if I did the following, if I took your quantum circuit to the 1 state and I applied that same brick that created 0 and 1, what would you expect? So again, let me remind you, when I started with 0 and I applied the brick called H, I got 0 and 1 with equal proportions. When I take the qubit and I turn it into the 1 state and I apply that again brick, this time I get something that looks like 0 and 1. But now the color is different. And the color is different because there's now a phase on 1. 1 has a minus sign in front of it. This is something you totally can't do on a classical computer. This is a new rule that I just inserted into your rules of computation. I just told you you can create a state that has positive and negative weights. And in fact, this is the part that always like blows my mind. If you take the same Lego brick and apply it twice. So let me remind you again what I did. I went from 0 to this brick takes me to 0 plus 1. If I apply that same brick again, it actually takes me back to 0. Why does it take me back to 0? How did we end up from 0 plus 1 all the way back to 0? And the answer is because this one with 0 and 1 with a minus sign around 1, and this one with 0 and 1 with a plus sign around 1, cancel out in such a way that you have interference between the quantum states. And so at the end of the day, what you get is just something that's purely in the 0 state. And first of all, these are all like, I'm going very quickly here, but the point is to tell you, like, the rules of the game that I'm using here, superposition is the ability to create these 0 plus 1s, and interference is the ability to take phases that are positive and negative and add them together and make them cancel out, are completely new rules. They're the rules of quantum mechanics that you're using for your computation. And in fact, it's not just fun in games. I'm taking this quantum circuit that you're looking at right here, and I'm running it on a quantum computer right now. And I'm queued number 3 to be able to run it on that quantum computer. Ooh. So I'll show you the results that you'll get when you run this on a real quantum computer. But running this on a real quantum computer is as simple as going to the IBM Quantum website and registering with an account, getting your API token. Once you have your API token, look at what I'm doing. I'm just loading my account from here. And I'm pulling a quantum computer, and I'm executing the circuit on the quantum computer. In like 2 lines, I'm building a quantum circuit and running something immediately on a quantum computer. And I'm waiting in line in order to be able to get the results back. So this answers both Rob's question and Susanna's question. It's not just like fun and games. I'm able to build out this logic, starting with quantum mechanics, the rules of quantum mechanics, and then deploy it on a real quantum computer and then get the results back. And obviously there are queues, but there are, of course, so many of these quantum computers that these queues don't take too long in order to be able to get the results back.
That's so cool. This
Yeah,
is super.
thanks for
I mean,
that
Faye, you
demo.
do more of this than I do, right?
Well, I mean, not quantum computing. We'll work with our classical computers here, but no, that was a really cool demo on describing how, you know, there's the foundational different logics between the classical computing and quantum computing. I'm curious, like, what are overall applications that quantum computing can reach that classical computing can't? Like, you showed the foundational logics. I guess in the next higher level state, what can quantum computing application-wise do that can extend classical computing?
Yeah, so what I just showed you is the process of building out a quantum circuit, which is like building out the Lego bricks. The next question becomes, how do you make quantum algorithms? And the quantum algorithms at the end of the day are going to be using these pluses, minuses that I showed you, and something that I didn't show yet called entanglement between multiple qubits, and then building out to do something meaningful. And the motivation for quantum computing from very early on was actually to be able to simulate quantum mechanical things with quantum mechanical things that we can control and leverage. So this quantum computer at the end of the day that I'm working with is actually using the principles of quantum mechanics. So potentially I could use it to simulate another quantum mechanical thing by adjusting its settings to be very similar to the other one. So one immediate application that comes to mind is in problems like chemistry, where you're trying to find the ground state of a molecule or something similar to this. The other place where quantum computers have a lot of promise, something that this is the thing that got a lot of people excited to join the field. In the 1990s, a new algorithm called Shor's algorithm came into the picture. And it's an algorithm that can run on a quantum computer. And it's an algorithm that can factorize numbers on a quantum computer. Now, factorizing numbers, if I give you the number 15 and I ask you to factorize it and you say, oh, 15 is made up of 3 and 5. 3 times 5 gives me 15. That problem of factorizing, going from 15 to 3 and 5, is a very difficult problem to solve on a classical computer when the numbers are very large. It's actually so difficult that it's the basis for the security of our internet today. When you communicate with your banks, that's how they encrypt the communication. Shor's algorithm shows that you can factorize large numbers in polynomial time, almost polynomial time, on a quantum computer, which puts your internet security at stake. Now, granted, Shor's algorithm needs a lot of qubits, and we don't have that many qubits today. You immediately start to see that quantum computing has significant impact potentially, and we need to explore a lot of these applications. So that's another algorithm that's very useful for doing something meaningful. At the same time, and I think this goes into the discussion that we're having just before this call started, is it's so useful to explore the applications of quantum computing in various industries. And to be honest, the field is so young that we don't know what all these applications are. And so we're in the phase where bringing in people from all over the world is very important to be able to explore more applications for quantum computing. And that, I guess, takes me to the point of really making these quantum computers accessible to everyone. That's why it's critical that it's not just fun and games accessing these quantum computers online. It's that we're really exploring ways to take problems that we're trying to solve today and map them onto quantum computers and potentially look for advantage by running on these quantum computers.
That's so cool. Yeah, and that's a great segue to the other part of what we want to talk about, of this idea of inclusion and diversity. And I think it's really interesting that you bring up this idea of literally like spatial include, like allowing people to engage in this who aren't at the one of some number of places where you can actually, go and touch the computer or the case that it's in, but rather like this sort of advancement is so important. And so one of the questions that came in was actually, so doing work in diversity and inclusion is often seen as time by many. Basically, you might be told that this is not a serious part of your work, like focusing on diversity and inclusion. Is this really important? So the question is sort of when people say, okay, like, is diversity and inclusion important in your field? What is your kind of response to that?
Yeah, so diversity and inclusion is always important. Let's just start with that fundamental premise. There's never a point where it's not important. But here, if you think back to computing revolutions, if you think back to phases where technology has progressed because something new happened, typically the pattern is something like the discovery is found in some place, and people who are well positioned to benefit from that discovery benefit really, really quickly. And the distribution of that technology takes a long time to benefit certain parts of the world. It's not evenly distributed across the world. And this has been the pattern for pretty much any technology that you can think of. In quantum computing, we actually have a huge opportunity here to flip that narrative and to start with access for everyone from the very beginning. And that's what makes me really excited about working in this field. So, as I mentioned earlier, in the interest of finding applications for quantum computing, it's very important to have multiple perspectives in the field. And so diversity and inclusion is important from the perspective of having different expertise coming into the field, from the perspective of opening up access all around the world so that people are contributing to this from all over the world. The one thing I'll mention here is that there are many problems that are very sort of regionally focused that we wouldn't be able to think of if quantum computers were accessible to very few places around the world. It's too early in the computing technology as it stands today for us to limit access to quantum computers, because there's just so much potential to discover here by opening up that access. So the question about diversity and inclusion is all about, one, empowering people to explore quantum computing so that they can contribute to the field. Two, bringing in different perspectives from different fields. The key here is to enable everyone from all around the world to program on these quantum computers. And as I showed you, all you need is an internet connection. So in this regard, let me, I guess, share with you a quick story here. In year 4 of grad school, I traveled back home to Ethiopia, and I was trying to decide between, this narrative of when you join grad school, you're always asked, like, are you industry or academia? Where do you want to end up, kind of thing. It's really not a simple choice like that, but that's kind of what you hear. I did not know the answer to that, so I went back home to look at universities to see if I could set up a lab to do experimental quantum computing work. And it became really obvious that building a quantum computer, which is an endeavor that takes several hundreds of thousands, maybe even millions of dollars, is quite challenging to do in a place that has very few resources financially in that regard. So my strategy changed to somehow trying to make quantum computing accessible to places where it's very difficult to build. And fortunately, this aligns with what I'm doing today, which is trying to open up access to quantum computers, just like you saw, through an internet connection. Now, anyone, including people from my home country, can participate in this quantum computing revolution. All it takes is an internet connection, and that's something that's much more accessible than having to build $1 million equipment close to you.
That's so cool. It's really interesting to hear how diversity and inclusion perspectives can differ with the field. And what is interesting to me is how you're really talking about distributing these resources. And I think in a lot of discussions that I've jumped into about diversity and inclusion, it's a lot about how do we focus on our local environment so that people feel welcome coming in. And it's this other perspective of also how do we distribute resources to people who might not have access to resources is a really interesting perspective that I think is so important overall. And it makes sense how it's a big perspective to keep in mind in quantum computing. And it's really cool to talk to people in different fields and to see how diversity and inclusion approaches to that can differ depending on the field.
Right. And my hope, so I guess there are two goals. One is opening up access. The other is for the few scientists that we have in the field from different corners of the world where there isn't majority representation in the field right now. It's also important to make an environment that's inclusive. And so for example, I have some breaking news. It turns out I'm Black, and I'm a Black person in quantum computing, and I think there aren't a majority of Black quantum scientists and engineers. One of the things that I'm very excited about is creating a home for people to come join the field. If you see someone who looks like you who's in the field, it's also something that you can aspire to. Even if I show you that a quantum computer is accessible, it's much more powerful to see people who look like you using these quantum computers. So that's, you might have seen this initiative called Black in Quantum on Twitter. That's something that I'm really passionate to see succeed, because opportunities like mentorship and guiding people to go through the grad school application to learn quantum computing, all of them are in an attempt to bring quantum computing closer to people and make not just the access, but to also bring a welcoming environment, give people a welcoming environment as they join the field.
Yeah, and I think another overlap with the topic of diversity and inclusion is also imposter syndrome. So we have a question here that was submitted on social media that says, do you ever deal with imposter syndrome and how do you get over it? And this is, I think, a common question that we've seen throughout so many of our grad chats, but I think it is always interesting to hear how people from different fields with different experiences, what is their response to dealing with imposter syndrome?
Yeah, this imposter syndrome takes me back to the first couple of years of grad school where I really, really struggled with that one. And I think at the end of the day, what it comes down to is having mentors in the field, people that you can talk to about your path, is very important. And whenever you feel imposter syndrome, it's very important to be able to have a sounding board that you can talk with. This is why mentorship is very important in fields like quantum computing. At the same time, for me, every time I thought of maybe not feeling as well equipped as others in my field, my primary thought process is something like they got where they are because they worked really hard. And the solution for fixing this imposter syndrome is to work really hard. And so I always focus my efforts to putting in time to learning new things every time I feel a little bit of imposter syndrome. And it's rewarding when you do it that way, because you'll find out that you're taking actionable steps to really fixing your imposter syndrome. Eventually, you'll make enough of a contribution to the field that you won't feel this imposter syndrome anymore. But the goal is to try to give yourself, are these called like dopamine hits or something like this, where you kind of put little grains in the sand for yourself to pick up along the way? If it's quantum computing, a really cool way to not feel imposter syndrome is to look at the source code, the quantum computing software, which is open source, to look in all of the resources that we have online. They're all open source and open access, which means you can go and make a contribution. You can literally change the software that I was using earlier to write code. And I think making impact in that way can make you feel like you're part of a global community and you're making change.
That's amazing. That's so cool. I mean, I feel like I've heard a lot of different perspectives, but I love that point of, I think there's the side of like, you have to let go a little bit, but then also finding those pieces you can have control over, and finding those pieces of like, you know what, I'm going to keep contributing. And then being mindful of realizing what you've contributed and things like that. That's so cool. I want to make sure to get to this question, which especially now, I think Faye and I, and probably everyone watching has. This question says, you seem to be doing so much. How do you deal with it all? And how do you make sure that you get downtime? Like how do you do all of this? This is a ton of stuff. And even you started out saying you had all these different passions, and it turned out that quantum computing was that kind of marriage of all of them. Yeah, how do you do this?
So one thing, you mentioned downtime. I am very aggressive about my downtime, and protecting it from sort of being taken over by other activities. One of the discussions that I always have with people is about how you block time so that you can think about new things. I had this conversation with my uncle once where he said something along the lines of, hey, call me when you have any free time. And I remember replying, every time I have free time, I spend that time feeling guilty for work that I'm not doing. So I don't have time to just kind of think about, who should I call in that free time? And I remember thinking at that moment that downtime, if you're spent being guilty about work that you're not doing, is not downtime well spent. Downtime well spent is when you're actively making sure that your brain is not thinking about something that worries you. When you're giving yourself some brain food, whatever it is that makes you happy. And for me, brain food is going and reading how people are making new quantum computing hardware, learning about the new tricks that people are playing in the lab to do something really cool. But whatever it is for you, unlocking that brain food and finding out how it works and really giving yourself time to consume that brain food is important. The other thing I really like to do and enforce in my downtime is I like listening to electronic music. I DJ'd in grad school to keep sane, and listening to the tricks that people use to mix, synchronize different tracks together is something I really pay attention to. And in my downtime, I spend a lot of time trying to master how people do that. But beyond that, in terms of the work that I do on a daily basis, I think it's very important to be coupling your research work with outreach and teaching others and bringing people closer to the research. And so it might seem like research and teaching and outreach and building an education effort are kind of multiple missions, but really they're all tied together. As I'm learning about how to simulate X on a quantum computer, I'm thinking about how to teach it to someone who may not know this. And the best person who's able to teach others is the one who's going through the learning process now, because they know the difficulties of going through that process. So within every step that I do to try to learn something on my own, you'll also see kind of this branch of, how do I teach this to someone else? How do I bring someone else closer to this field? I think those are the only tricks that I have. There isn't much else.
I think that's amazing. Yeah, I love the part of being, I think you said, aggressive with your downtime, which is amazing.
Yeah, this has been awesome. We're running out of time for our grad chat, but Abe, if there's any other topics that you want to bring up that we haven't talked about yet, anything that comes to your mind that you want our viewers to hear?
Yeah, so I think the main thing I want people to know is that a field like quantum computation can benefit from all of your perspectives, and potentially we're going to be able to find a quantum application that we don't know about today because you joined the field. And so please do join the field, see how you can run quantum computers and potentially even learn how to map the problems that you study onto a quantum computer. If you quickly Google learn quantum computation using Qiskit, Qiskit is Qiskit. That's a textbook that we've put together online for you to learn quantum computing. It shows you snippets of code that you can run on a real quantum computer, which I still to this day cannot believe that you can just kind of copy paste code and run it on a quantum computer. So do join the field, explore quantum computing. I always talk about quantum computing on my Twitter, which is at Abe_Asfaw. Otherwise, please do also bring in more people into the field, and let's make this an inclusive and global community. That's what excites me. Yeah.
Oh, this is so cool. Okay. Well, I wish we could talk to you forever. Definitely encourage people to follow you on Twitter, reach out that way. But just wanted to say, one more time, echoing what Faye said, thank you for coming on. Thank you for doing all this work. Thank you for taking your time to not just educate us, but also so many people all over the place who are going to be benefiting from this. And the fact that you're doing this like at a global scale, that's awesome. But thanks again for joining us, Abe.
This has been awesome. And I've watched past grad chats. It's awesome to be talking with you and to be inspired by you as well. So thank you.
You're sweet. Okay, I'll take that warm fuzzy. All right, bye.
Bye, everyone.
Okay, it says it's ended.